In this video, we're going to introduce the idea of support vector machines for performing classification. We'll begin by defining the margin for separable data, and then show that support vector machines identify decision boundaries that maximize margin. Then for the case of non-separable data, we're going to use hinge loss to define a support vector machine classifier. Now, a useful principle is to maximize the margin when you have separable training data. So let's suppose we have some data as shown here. It's just a set of scalars, and we want to classify this into a class with labels -1, the blue dots, or a class with labels +1, the red dots. Where should we draw the decision boundary? Well, any boundary in this interval will adequately separate the training data. Now we define the margin as the distance from the boundary to the nearest training sample. So what I've shown in pink here is the max margin boundary, and that's the midpoint between A and B. Now that seems like a reasonable thing to do because we're eventually going to classify data that we don't have in the training set, and some of that could lie to the left of B or to the right of A. And by putting this boundary in the middle, we are trying to get the best performance in the absence of any other information about the distribution of the training data. Now, it's also interesting that for this classifier, the only two values that matter are the samples at points A and B. Now, if we extend this idea to more than two dimensions, we see that in general, it's a little bit more complicated. If I have this data here shown in blue and another category shown in red, I could use any of these planes to separate the data. Now the one that maximizes the margin is the one that kind of splits the difference here, and it's equidistant from all the points that are nearest to the boundary. So we'll define some terms that we need to find the max margin decision boundary. Recall that we have features x, and we're going to decompose x into a component that consists of the data and the constant. Recall that we often add a constant in order to shift the boundary away from the origin. Without the constant, our decision boundary for a classifier of the form x transpose w has to go through x equals 0. We'll also use our classifier weights w and partition those in terms of w tilde transpose and w0, the constant that's associated with this offset. We choose a label given by the sign of x transpose w, and that produces a label of 1 when x tilde transpose w tilde plus w0 is greater than 0, in other words, on, say, the right side of the boundary, and a label of -1 when x tilde transpose w tilde plus w0 is less than 0, so that's on the left of the boundary. It turns out that the margin, or the distance from the decision boundary to the closest points on each category, is determined by the 2 norm of w tilde inverse. Now to see how this works, we're going to assign label 1 whenever x tilde transpose w tilde plus w0 is less than or equal to -1. So we're calling that the line that is on the edge of the category with label -1, and then we'll have another boundary on the edge of the category with label +1, and that will be defined as x tilde transpose w tilde plus w0 greater than or equal to 1. And then the decision boundary splits the middle of those two things, so that's going to be x tilde transpose w tilde plus w0 equals 0. Now the assigning of values 1 and -1 here is somewhat arbitrary, but you can see that clearly this decision boundary, we can multiply w tilde and w0 by some constant without changing the boundary. So I multiply on the left by the constant, on the right that constant does nothing because I have 0. So I can always adjust the norm of w tilde and w0 so I get either 1 or -1 at either edge. And that turns out to make this problem a little bit more convenient to solve algebraically. Now the margin is half the distance between these two lines, but we have to measure that distance in the direction perpendicular to the boundary. So we'll define the unit normal to this boundary plane, and that's given by a vector v, which is w tilde normalized. Ignoring the shift here for a second, the boundary x tilde transpose w tilde equals 0 implies that it's a set of vectors orthogonal to w tilde. So a vector orthogonal to the boundary is given by anything in the direction of w tilde. So we can solve for the margin now. If I put some point on the two boundaries, say x1 tilde on the boundary for category 1 and x0 tilde on the boundary for labels with -1, then my margin is half the separation between those two. And we know that x1 tilde then can be written as x0 tilde plus 2 times the margin times v. So v gives me the direction of x1 tilde relative to x0. So then the distance that we're going to travel in the direction of v when we go from x0 tilde to x1 tilde is 2 times m. Now I know that x1 tilde is on the boundary. So 1 is equal to x1 tilde transpose w tilde plus w0, and I can substitute for x1 tilde the expression that I derived previously. So then I end up with x0 tilde transpose times w tilde plus 2 times m. Now we replace v by w tilde divided by the 2 norm of w tilde. And so I'll have w tilde transpose w tilde divided by the 2 norm of w tilde. And then we have the plus w0 that we add in. Of course, we know that x0 is on the boundary for categories with label -1, and therefore x0 tilde transpose w tilde plus w0 has to be equal to -1. So I can replace this term, the w0 and the x tilde 0 transpose w tilde, with -1. And here I have w tilde transpose w tilde divided by the norm of w tilde, and that's just the 2 norm of w tilde. So if I take the -1 that I put in here for w0 plus x0 tilde transpose w tilde, and I move it to the other side of the equation, I end up with 2 is equal to 2m times the 2 norm of w tilde. And therefore, I can conclude that my margin m is the inverse of the 2 norm of w tilde. So support vector machine chooses the decision boundary to maximize the margin subject to correct classification of every sample, in this case where we have separable data. We can write the condition for correct classification as di times the quantity xi tilde transpose w tilde plus w0 is greater than or equal to 1. So we have these boundaries on the two classes, and the one with labels +1 boundary is xi transpose w equals 1. So if I have a point on the boundary, then that corresponds to xi transpose w equals 1, and di in this case is +1. So this point satisfies this condition with equality. If I take some point that's to the right of the boundary, in this case xi transpose w is greater than 1, so when I multiply by di, which is 1, I get a number that remains greater than 1. For the samples with labels -1, we have something very similar. So if we're on the boundary, we know that those samples satisfy xi transpose w is equal to -1. Well, di in this case is -1, so when I multiply that, -1 times -1, I get exactly 1. So when I'm on the boundary, I have equality, and then when I'm to the left of the boundary, here I have xi transpose w is less than -1, so when I multiply that by -1, it ends up giving me a number which is greater than 1. Hence, we can write the support vector machine criteria or design problem as shown here. We're going to maximize the margin. Remember, the margin was related to the inverse of the 2 norm of w tilde. So instead of maximizing the inverse, we'll minimize the 2 norm squared, and that maximizes the margin. And then we'll have these constraints that we have perfect classification. In other words, di times the quantity xi tilde transpose w tilde plus w0 is greater than or equal to 1 for every training sample. Now this is a quadratic minimization problem subject to a set of linear constraints, and this has a unique solution, and it's not too difficult to find. Now the decision boundary, it turns out in this case, only depends on the training samples xi that define the edges of each class. And that occurs when di times xi transpose w equals 1. So these xi that satisfy this condition are the ones that lie on the boundary, and they're called support vectors. So in this illustration here, we have three support vectors. We have the one up here on the category -1 label, and then we have one to the lower part for the category -1 label, and then over here on the right for the one with category +1. Those are the support vectors, and that's the reason for the name support vector machine. Now, in order to extend the support vector machine idea to non-separable data, we use the hinge loss. So we find a classifier set of weights W that minimize the sum of the hinge loss and lambda times the inverse of the margin squared. Now this is just an L2 regularized problem, but the interpretation here is that we're trying to balance the size of the margin by making the 2 norm of W small against hinge loss, which we also want to make small. So let's look at the case where the data is not linearly separable, as I've drawn here, and what I've shown is some data with labels -1 in blue, labels +1 in red, and then our optimal boundary as defined by our support vector machine in green, and then our margin between these two lines drawn in light orange. If I have a red point to the right of this orange boundary, these contribute nothing to the hinge loss because these are cases where xi transpose times w is greater than 1 and di is equal to +1, so this difference in the hinge loss is negative. Similarly, if I have labels -1, the blue points, to the left of my orange boundary, these are points at which xi transpose w is smaller than -1 and di is -1, so this difference is also going to be negative and it contributes 0 to the hinge loss. I've illustrated two cases that contribute to the hinge loss in red. So this point that I've shown here is to the right of my decision boundary. So this would be a correct classification, but xi transpose w in this case is less than 1. And so this difference is going to be positive, though small, and that point will indeed contribute to the hinge loss. I can't separate this data using a linear classifier, so this one's going to be a misclassification. So what the support vector machine does is it balances these hinge losses against the size of the margin. And our parameter lambda determines how these two things trade off. For example, I might have data which is linearly separable, and if I use this hinge loss approach, I could consider two different cases. So I could separate the data completely using the light blue boundaries here, and in which case my margin again is the distance between these two boundaries, and I would have 0 hinge loss, but because my margin is relatively small, the second term would end up being large. When lambda is large, I'm saying that margin is more important than the hinge loss, and therefore I'm going to tend to tolerate some hinge loss here in order to get a larger margin. On the other hand, when lambda is small, then I'm going to say that my loss is more important and the margin is not as important, and so I'm going to end up with a solution that has a smaller margin. Support vector machines are very powerful and are widely used for classification. In the next video, we're going to develop an proximal gradient-based iterative algorithm for solving this sort of optimization problem, particularly when the loss is not differentiable.